At the peak of modern manufacturing, success looks like blinding speed. We engineered smart factories where robotic arms execute flawless, rapid sequences in total isolation, operating well beyond the limits of human physical endurance. This chart tracks the evolution that got us here, progressing from the steam power of Industry 1.0 up through the heavy automation and digitalization of Industry 4.0. The overarching goal of industrial engineering has been the systematic elimination of friction. The 4.0 model achieved this through the Internet of Things, massive data analytics, and decentralized machine-to-machine communication. The system evaluates data and executes production decisions autonomously, entirely removing the human bottleneck. But removing friction also removes flexibility. The first structural failure of this highly tuned model is its extreme vulnerability to supply chain shocks. When a global disruption occurs, rigid optimization prevents the system from adapting. The second failure is externalized cost. Powering continuous data centers and manufacturing connected sensors generates a massive environmental footprint, while simultaneous aggressive automation displaces the human workforce. When an industrial architecture is engineered exclusively to maximize efficiency, it becomes brittle. It lacks the margin for error required to survive unpredictable modern disruptions. Industry 5.0 re-engineers the 4.0 optimization algorithm to directly address this structural brittleness. This diagram maps the resulting framework. Instead of solving purely for productivity, Industry 5.0 demands that systems balance output against three new foundational pillars: human centricity, sustainability, and resilience. Sustainability demands that the factory optimize its resource usage. This involves integrating circular economy principles to aggressively reduce waste and environmental harm. Resilience requires systems designed with built-in elasticity. They must be capable of absorbing external macro shocks, like pandemics or material shortages, and recovering quickly without catastrophic operational failure. Finally, human centricity redirects the purpose of the technology itself. Instead of designing machines to replace human labor, engineering efforts are focused on enhancing human cognitive and physical capabilities. The definitive test of an Industry 5.0 architecture is its control loop. If the system successfully moves the human worker from the obsolete periphery back into the center of decision-making, it meets the standard. Executing that standard introduces a severe engineering paradox. You have to safely merge unpredictable human creativity with rigid machine autonomy in a shared physical space. We can map the solution to this paradox across this 5-stage framework of human-robot collaboration, or HRC. Level 1 is the legacy approach: fenced robots. Safety is guaranteed purely through physical isolation. A steel cage separates the human from the machine. While safe, this creates a severe productivity limit. Cages consume massive amounts of factory real estate and prevent managers from making rapid adjustments to the workflow. Level 2 introduces coexistence. The physical cage is removed, and human and machine share the same open environment. However, their tasks remain strictly independent. The human and the robot operate side by side, but their actions are completely decoupled. In both Level 1 and Level 2, the system protects humans by treating them as hazards to be avoided. That defensive posture inherently caps the factory's overall productivity. To increase output, operations must advance to Level 3, sequential collaboration. Here, the human and the machine begin to share a workflow.
They operate on the same component, but they do it sequentially, passing the work back and forth at defined handoff points. Level 4 pushes this into cooperation. Humans and robots interact simultaneously, working on a shared task within the exact same physical space. This creates a critical technical bottleneck: cloud latency. If a robot relies on a distant data center to process its safety sensors, the round-trip signal delay is simply too slow to stop a mechanical arm if a human makes an unpredictable, sudden movement. The solution relies on edge and fog computing. Instead of sending data out to a distant server, the processing power is relocated directly onto the robotic joint or the local factory floor. This localized, zero-latency processing enables the deployment of true collaborative robots, or cobots. They can read sensor data and adapt to physical impacts in real time without hurting the operator. Deep physical collaboration on the factory floor is strictly bound by the speed of localized data processing. Which brings us to the pinnacle of the framework, Level 5, Responsible Collaboration. At this stage, machine learning algorithms upgrade the system. The cobot moves past reactive collision avoidance and begins proactively predicting human intent. This relies on digital twins, virtual copies of the factory floor running continuous, real-time simulations. The system tests millions of potential paths to optimize task allocation before the physical robot even moves a gear. But this introduces a psychological bottleneck. When a machine makes autonomous, predictive decisions, the human operator's trust in the system frequently breaks down. As this graphic outlines, the 5.0 model transforms ethics into a mandatory engineering framework. It requires transparency, so choices are explainable, algorithmic fairness to ensure unbiased task allocation, and strict accountability, so the human always retains the ultimate agency to override automated processes. At the highest levels of Industry 5.0, moral values must be explicitly coded into the machine learning architecture. If they aren't, the human-machine relationship deteriorates and the system collapses. That is the pristine academic theory, but the reality on an actual operational factory floor is far messier. While the EU Commission pushes broad macroeconomic ambitions, small and medium enterprises experience severe friction when attempting to adopt these frameworks. Field data from the Prospect 5.0 case studies reveals the first major barrier: integrating highly advanced machine learning cobots with outdated legacy factory data systems. The new nodes simply cannot interface with older databases. The second barrier is financial. Building the localized edge computing infrastructure required for zero-latency robotics demands extreme upfront capital expenditure. The third and most critical barrier is a severe shortage of personnel possessing the advanced digital skills required to manage these hybrid ecosystems. This exposes a core paradox of the transition. Achieving seamless, human-centric automation ironically requires a massive influx of highly trained human experts. Industry 5.0 cannot be purchased and installed like a software update. It requires a painful structural overhaul of a company's financial allocations and cultural metrics. The trajectory of manufacturing has shifted. The primary goal is no longer building faster, isolated machines, but building adaptive, sustainable nodes. The ultimate limit on future factory productivity is no longer the physical speed of its robotics. It is how successfully the architecture integrates with the humanity operating it and the environment sustaining it.